And also, of course, most people wouldn't particularly want to be working with rats that they're poisoning. Now I move to another way of testing morphic resonance, in this case in cell biology. And this is based on a phenomenon called the Hill effect, discovered by a French biologist called Miroslav Hill, working at one of the French state biology laboratories. Hill discovered that if you take normal tissue culture cells, mammalian cells in tissue culture, and you grow them in a toxic medium, or you grow them in extremely high temperature, that's the limit of what they can stand, after a number of generations, some of these cells acquire the ability to survive in these conditions. Now, he discovered this through experiments in which he subcultured the cells from petri dishes or test tubes from the normal medium to normal medium to normal medium, generation after generation. But some of them he put in a medium containing toxins, or at high temperature. The shaded circles you see there represent the stressed conditions. What he found was, after a number of generations, they started surviving in these stressed conditions. And once they'd started surviving, generation after generation, they continued surviving. They got more and more resistant to the toxin or the high temperature. And he thought this must be because of mutations, but there was no way in which the stressed cells could influence the line that's being propagated, because they weren't being bred from. The only cells being propagated were ones that had never seen the stress, and yet they were responding as if they had, as if they had benefited from an adaptation acquired by the cells in the stressed petri dishes. Well, Hill tried to explain this. He was very baffled by it. He repeated the experiment with different toxins, different kinds of cells, and different heat stresses over and over again, and found it was a repeatable phenomenon. He didn't call it the Hill effect. Subsequent people call it that because he was the person who discovered it. And his interpretation was that in some way the cells are somehow entangled through some kind of quantum entanglement. So the ones that have learned to adapt to the stress modify the ones that have never been exposed to it, which pass on the modification to the next generation, which enable them to respond to the stress better. Well, there's no evidence for quantum entanglement in biological systems of this kind, and he admitted this was a very speculative explanation. But my own explanation, in terms of morphic resonance, is different. I think that the cells that have learned to adapt could directly influence subsequent batches of cells that are adapting to the same stress by morphic resonance, and the more that have done it, the greater this influence would become, the stronger the Hill effect would appear to be as time goes on. Well, I think this is a very fascinating experimental system because, apart from anything else, it tells us about the biological ability to adapt to stresses, and this is of great importance in ecology, climate change, response to toxic chemicals in the environment, or even the deliberate breeding of organisms that can deal with toxic chemicals in waste dumps and in the environment. So I proposed an experiment to test the Hill effect, which is summarized in this diagram here. In one case, the cells are treated as Hill did in every generation exposed to the stress you see along the lower line. But in the upper line, for the first, say, 4 or 5 generations, they're not exposed to the stress, and then they're exposed to the stress. Now, his entanglement theory would mean that the ones in the top line wouldn't be entangled by stress cells for quite a number of generations, however many you choose to do it without the stress. And then when you start exposing them to the stress, it might take 5 or 10 generations, if that's what it took the first time round, for this effect to show up. But if morphic resonance is at work, it should show up much quicker. You shouldn't have to do it so often. It should happen more readily, even though the cells you're testing are not entangled, quantum entanglement, with those that have already been tested. Now, this may sound a little bit complicated and technical, but actually the experiment in principle would be quite simple to do, and they could be done in quite simple laboratory conditions. You don't need a very, very advanced lab to do this. In fact, even in a school lab, you could probably do these kinds of experiments.